Arizona's rocks are red. Everyone sees it. Almost nobody knows why. The answer goes back further than dinosaurs, further than Earth itself, and it starts with a single mineral so powerful it can color an entire mountain range. At number 10, we have the one mineral responsible for all of it, hematite. It is an iron oxide compound, the same chemical reaction that turns an old nail orange when it gets wet. Iron bonds with oxygen and produces a pigment so strong it bleeds through entire cliff faces. The chemistry name is Fe2O3, and the word hematite comes from the Greek word for blood. That connection is not poetic, it is accurate. The color it produces ranges from brick red to deep crimson, depending on how thickly it coats the rock around it. Here is what makes hematite so unusual as a pigment. It does not need to be thick to work. A coating barely visible to the naked eye, covering individual grains of sand, is enough to turn an entire canyon wall the color of dried rust. One thin film. Total transformation. Hematite forms specifically when iron meets oxygen in the open air or in oxygenated water. That means the red color in sedimentary rock is actually a record of exposure. The rock was sitting in the open, breathing, before it got buried under the weight of everything above it. Without hematite, every famous red formation in Arizona would be a pale gray or off-white. The Sedona Canyon walls, the Grand Canyon layers, the Painted Desert, the Vermilion Cliffs, all of it, white quartz sandstone stained by a single iron compound less than a millimeter thick. Hematite is not evenly distributed across Arizona's rock. It concentrates in layers and patches depending on where iron-rich water traveled through the rock over millions of years. That is why some walls are deep red, while others in the same formation show streaks of orange, pink, or tan. This one mineral, formed through the same basic chemistry as rust on a car door, is the answer to one of the most asked questions about Arizona. Everything else on this list is built on top of that single fact. Hematite is where it starts. Coming in at number 9 is the landscape that made this all possible in the first place. Long before canyons existed, long before any of these formations had names, a massive desert covered this entire region. Not a small desert, something close to the size of the present-day Sahara, but older. This ancient sand sea stretched across what is now the American Southwest during the Jurassic period, roughly 180 to 190 million years ago. The dunes were enormous, the sand was deep, and the conditions were almost perfect for turning raw iron into hematite on a massive scale. Here is how it worked. Along the edges of that ancient desert, shallow oxygen-rich water sat in contact with iron-bearing sand. The iron in those grains reacted with the dissolved oxygen and slowly converted to hematite, grain by grain, layer by layer, across millions of square miles. Over time, those rust-stained sands got buried. More sediment piled on top. The weight compressed everything. The sand grains fused together, and the hematite coating, already locked onto each grain, got cemented permanently into what we now call sandstone. The red color was sealed in before the rock even formed. The name for that rock layer is the Navajo Sandstone. It is preserved across a huge stretch of the Colorado Plateau and reaches up to 2,500 feet thick in some locations. It is the direct product of that ancient sand sea, and it is still visibly red and orange across much of northern Arizona today. Geologists can read the original dunes inside the Navajo Sandstone by looking at the angle of the layers. Those tilted lines inside the rock are called crossbeds, and they show exactly which direction the wind was blowing across that ancient desert more than 180 million years ago. That ancient desert is not just background history. It is the original red canvas that Arizona's geology was painted onto. Every famous formation that sits above it built its color on top of a foundation that was already stained red before any of it existed. Number 8 is where the red rock story gets a face that most people already recognize. Sedona. It draws millions of visitors every year, and the color of its canyon walls is almost certainly the most photographed red rock scenery anywhere on the planet. But the specific reason for that color has a name most people never hear. The formation responsible is called the Schnebly Hill Formation. It is the dominant rock layer that makes up what most people simply call Sedona's red rocks. It runs 800 to 1,000 feet thick, and its deep color comes from hematite staining white quartz sandstone, the same way rust stains pale metal. The story of this formation goes back over 300 million years. The Sedona area was a dry coastal plain sitting beside a shallow sea. Wind moved sand across the surface. Rivers carried sediment down from higher ground. Ocean currents pushed material in from the water. All of it piled up in layers. As sea levels rose and fell over millions of years, the exposed sediment dried out between flooding cycles. During those dry periods, iron in the surface grains oxidized in the open air and formed hematite coatings. Then the next flood buried those stained layers, and the process began again above them. That repetition over millions of years built up a formation so thoroughly stained with iron oxide that the color is now structural, not surface. You cannot wash it off. You cannot sand it away. The red is inside the rock at the grain level, locked in since before the dinosaurs existed. Sedona became one of the most photographed places on Earth, not because of anything that happened recently. It happened because of chemistry and tide cycles running on repeat for millions of years. That is what produces a canyon wall saturated in red so intense it looks artificially colored in photographs. The Schnebly Hill Formation sits on top of older red formations, and below more red formations. Sedona is not one red layer, it is a stack of them. And the next entry on this list is what sits directly beneath it, adding its own layer of color to the same landscape. Number 7 is the Hermit Formation. It sits underneath Sedona's more famous rocks, and most people standing in front of those canyon walls have no idea it is even there. It formed approximately 270 million years ago, and runs about 300 feet thick through the Sedona area. It is a dark rust color, slightly different in tone from what sits above it. The Hermit Formation is made of soft sedimentary materials including siltstone, mudstone, and shale. All three are iron oxide stained in the same way as the formations above and below it. But what makes this formation unusual is not just its own color, it is what it does to everything beneath it. Rainwater moving through the Hermit Formation picks up dissolved iron as it filters downward. That iron-rich water keeps moving. It travels down through the rock column and stains the formations below it, sometimes formations that are completely different in chemical composition from the Hermit itself. The Grand Canyon makes this visible in a dramatic way. The Redwall Limestone, which sits far below the Hermit Formation, is naturally gray at its core, but centuries of iron-rich runoff from the Hermit washing down over it has permanently stained its outer face a deep, uniform red that does not belong to the rock. This is one of the most important ideas in understanding Arizona's red rocks. The color you see on a cliff face is not always the color of the rock itself. Sometimes it is color that traveled down from a completely different formation sitting hundreds of feet above it. The Hermit Formation is the main reason that happens. It also means the red geology of Arizona is not static. Iron continues to move through rainfall, dissolving, traveling, and redepositing. The staining process that colored these rocks hundreds of millions of years ago has not stopped. It is happening right now every time it rains in northern Arizona. Number 6 introduces something that looks completely straightforward, but turns out to be the opposite. The Redwall Limestone of the Grand Canyon. You can see it from the south rim as a thick band of red running across the canyon walls for miles. Its name says red. Its surface is red. Its core is not red at all. The Redwall Limestone is a Mississippian age formation, meaning it was deposited roughly 340 million years ago. It forms some of the most vertical and resistant cliff faces in the Grand Canyon, dropping 500 to 800 feet in places. It is one of the most prominent single rock bands visible from any overlook along the canyon rim. Here is what the name does not tell you. Chipped behind the surface of the Redwall Limestone and the rock underneath is a dark brownish gray. It is a limestone, which means it is made primarily of calcium carbonate, and calcium carbonate is not red. The red on its face is entirely borrowed from above. The Supai group and the Hermit Formation sit above the Redwall in the canyon's rock column. Both are heavily iron-stained. Every rainfall carries dissolved iron oxide down from those layers and deposits a thin red coating across the surface of the Redwall below. That process has been running for millions of years. The result is a gray rock that looks completely red from a distance and stays that way permanently. No matter how much of the outer surface erodes away, fresh surface is exposed, and the iron-rich water from above stains it again. The Redwall Limestone is continuously recolored by the formations sitting on top of it. This is one of the most dramatic examples anywhere of iron staining working across an entire geological column. color generated in one rock layer, traveling down through time and water to cover an entirely different rock layer, sitting hundreds of feet below and millions of years older. Number 5 is the source of all that iron-rich runoff. Above the Redwall Limestone in the Grand Canyon sits the Supai Group, a sequence of 4 separate rock formations stacked on top of one another, reaching 600 to 700 feet in combined thickness. It is one of the most iron-saturated sections of the canyon wall. The Supai Group is composed of rust-red sandstones, siltstones, shales, and a few limestone beds. Running through some of those limestone beds is a red variety of chert called jasper, which adds its own deep coloring to the sequence. The entire stack reads as a near-continuous band of red from canyon overlooks. These layers were deposited between roughly 320 and 270 million years ago, during a period when this region kept switching between 2 environments. Shallow seas swept in, then retreated. Coastal desert conditions took over during the dry intervals. That alternating cycle is recorded directly in the rock. The iron oxidation in the Supai Group happened during the dry coastal desert phases. When the sea pulled back, the exposed sediment sat in contact with open air. Iron in those grains converted to hematite. When the sea returned, those stained layers were buried and preserved beneath fresh sediment. Geologists have found marine fossils inside the Supai Group, including brachiopods, corals, crinoids, and gastropods. Those fossils are evidence of the sea phases. The red iron staining in the same rock layers is evidence of the dry phases. The Supai Group holds both records in the same stone at the same time. The 4 formations of the Supai Group together form some of the most consistently red geology in the entire Grand Canyon. But their most important role in this story is as a continuous source of iron-bearing water, slowly feeding the layers below and keeping the Redwall's borrowed color alive. Number 4 takes us to the far northern edge of Arizona, close to the Utah border, where one of the most striking geological sites on the Colorado Plateau rises out of the desert. The Vermilion Cliffs, walls of stone reaching nearly 3,000 feet in some locations, colored a blazing red-orange across miles of exposed face. The base of the Vermilion Cliffs is composed primarily of the Monivea and Kayenta formations from the early Jurassic period. Both are made of iron oxide-stained sandstone and siltstone, and both get their color the same way as every other red formation in Arizona. Hematite coating on individual sand grains locked in during oxidation long before burial. Sitting on top of those formations is the Navajo Sandstone, the same ancient desert sand layer from entry number 9. At the Vermilion Cliffs, the Navajo Sandstone displays a wider range of color than almost anywhere else, shifting from deep red at the base to pale pink and near white toward the top of the formation. Those color differences within the Navajo Sandstone are caused by different iron minerals filling the spaces between quartz grains. Hematite produces the deepest reds. Goethite produces yellows and browns. Lemonite produces pale orange and tan. Where those minerals mix in different ratios, the color shifts accordingly. Inside the Vermilion Cliffs area is a formation called the Wave, a section of swirling cross-bedded Navajo sandstone where the original dune shapes are still visible in the rock after 180 million years. The vivid reds and oranges flowing through it are a direct product of those same iron oxide minerals shaped by wind and water erosion. The Vermilion Cliffs are so intensely colored because multiple red formations are stacked directly on top of one another with almost no interruption. Each layer contributes its own iron staining, and the combined result is a wall of color that looks almost impossible in the middle of an open desert. Number 3 covers a region that takes a different approach to color entirely: the Painted Desert. It stretches across northeastern Arizona from near the Grand Canyon to the Petrified Forest, covering an enormous arc of exposed badlands. And unlike the formations listed so far, it does not just produce red, it produces everything. The reds, purples, lavenders, and oranges all come from one specific rock unit called the Chinle Formation, deposited during the late Triassic period, roughly 200 to 225 million years ago. The formation is made of fine-grained siltstone, mudstone, and shale, all laid down in ancient lakes, rivers, and broad floodplains. The specific pigments come from 2 main compounds. Iron oxides produce the reds and oranges. Manganese compounds produce the purples and blues. Where those two overlap or appear in different concentrations, lavender, mauve, and deep violet appear. The painted desert is not one color because it is not one chemistry. It is both at once. The reason those colors are so visible today is that the Chinle Formation is made of extremely soft rock. Mudstone and shale erode fast. Wind and rain continuously strip away the surface, exposing fresh, unweathered rock underneath. That fresh material has not yet faded or been covered by dust and debris. It reads as saturated color. The painted desert does not have a final form. Every rainstorm removes a thin layer of material and reveals a slightly different arrangement of color beneath it. The surface you are looking at today is not the surface that existed 10 years ago. The landscape is always being peeled back to reveal what is underneath. And unlike the harder sandstone formations elsewhere in Arizona, the painted desert cannot hold cliffs or mesas for long. The soft rock rounds off into smooth curves, eroded badlands, and low ridges. The color is everywhere, but the structure is always changing shape. It is the most visually unstable landscape on this list. Number 2 explains why Arizona specifically ended up with the most visible red rock scenery in the country, when similar geology exists in other places that barely shows it. The answer is not just what is in the rock, it is what is not falling on top of it, and what is not growing over it. In wetter environments, iron in exposed rock often dissolves and washes away in a constant flow of rainfall and runoff. Or it reacts with different compounds in the wet soil and converts to iron minerals that produce green and gray instead of red. Humidity actively works against hematite's visibility. Arizona's dry, semi-arid conditions do the opposite. Long dry periods between rainfall events let iron oxide build up on exposed surfaces without being continuously flushed away. When rain does arrive, it washes dust off the rock face and deposits a fresh layer of iron-stained water across the surface, intensifying the color rather than removing it. The sparse plant cover is equally important. In humid regions, thick soil layers and dense root systems cover rock outcrops entirely. The red geology might be sitting right there beneath the surface, but it is hidden under meters of soil and plant material. You would never know it was red. In Arizona, thin desert soil and open terrain leave rock exposed directly to the sky. There is nothing covering it, nothing trapping moisture against it, and nothing acidic breaking down the hematite coatings. The chemistry that produced the red stays intact, and the dry air keeps it that way indefinitely. The cycle of occasional rain, followed by long dry periods, also drives a slow, ongoing oxidation process on exposed surfaces. Each rain event introduces a small amount of fresh, iron-bearing water. The drying cycle that follows concentrates it. Over thousands of years, those small contributions accumulate, and the red deepens. Arizona's climate is not just a backdrop for the red rocks. It is an active participant in maintaining them. The same geology placed in a rainforest would be hidden, chemically altered, or washed gray within a geologically short period. Arizona keeps it red because Arizona stays dry. Number 1 is where everything changes. Everything covered so far has been geology and chemistry and climate. But the deepest reason Arizona's rocks are red does not start on Earth. It does not start in a desert or a shallow sea or a river delta. It starts in space, billions of years before this planet existed. The iron that creates all of this color was not made here. Iron is not produced on Earth through any natural process. Every atom of iron on this planet arrived from somewhere else, and the place it came from is one of the most violent events the universe produces. Massive stars, far larger than our own sun, spend millions of years fusing lighter elements into heavier ones in their cores. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes heavier elements. The chain continues until the core is producing iron. At that point, the fusion process stops generating energy. Without energy pushing outward, gravity wins. The star collapses inward with tremendous force in a fraction of a second. That collapse triggers a supernova explosion powerful enough to outshine entire galaxies. The force of that explosion fuses elements together that could not form any other way, including large quantities of iron. That iron gets blasted outward into space along with everything else the explosion produces. It travels for millions of years as part of an expanding cloud of stellar debris, mixing with gas and dust from other dead stars in the surrounding region of the galaxy. Over billions of years, gravity slowly pulls clouds of that debris together. The material collapses into a disk of rotating gas and rock. At the center, A new star ignites. Around it, the remaining material begins to clump into planets. One of those planets is Earth, and the iron from those long-dead stars is inside it. That iron became embedded in minerals throughout Earth's crust during the planet's formation. It sat there for billions of years as continents shifted, mountains rose, and oceans formed and dried out. Then geological processes brought it to the surface. Erosion broke down the minerals containing it and released the iron. When that released iron met oxygen in water or in the atmosphere, it converted to hematite. In a shallow Jurassic Sea washing across what would become Arizona, in a Triassic floodplain, in a Permian coastal desert, in thousands of different environments at thousands of different points in Earth's history. Each time that happened, the iron locked into the sediment as a red stain and got buried. Each time those sediments became rock, the stain became permanent. The canyon walls you can see today from the South Rim or from a Sedona overlook are a direct record of iron reacting with oxygen across hundreds of millions of years. That iron traveled from a dying star, through billions of years of space, through the formation of a solar system, through the formation of a planet, through geological time measured in hundreds of millions of years, through ancient seas and deserts and rivers, through burial and compression and erosion, and it ended up coating individual sand grains and formations across Arizona with a layer of hematite so thin you cannot see it individually, but so consistent and so widespread that it colors entire mountain ranges. The same process that rusts iron on Earth is the visible surface of all of that history. Every red canyon wall in Arizona, every crimson mesa, every rust-colored cliff face is iron forged in stars that died billions of years ago, slowly rusting in open air across hundreds of millions of years of this planet's history. That is what the red color is. That is where it came from. That is what you are looking at.